All right, so now time for an experiment. Let me turn off that projector. Okay. So what I'm going to attempt, and again, this may not go well, but there's a proof in my notes, which is probably fine. But and maybe we'll be back to the proof in my notes in a few minutes. But I'm just going to try to derive the multivariate power series. See how much I can stand here. So the basic idea for the proof is just to exploit the fact that we have Taylor's theorem for a function of one real variable, and to try to try to use it. So let me see if I can get this set up right here. So what I want to consider, my goal is to find, the multivariate Taylor expansion for f, which is a mapping from Rn to R at x naught. All right, marker, you're dead to me. So towards that end, I am going to consider a path, let's say R of t, which is equal to x naught, all right, plus t times x minus x naught. So in this setup, we have R of 0 as x naught, and we have R of 1 as x. All right? And I'm going to consider g of t. And now the thing is, g of t, right, is going to be equal to f of r of t. I'm going to consider that composition. And in so doing, now I've got g as a mapping from where to where. Like r here r is a mapping from what? From r, right? Back to Rn. So if I compose f and r, I've got an honest to goodness mapping, g is a mapping from r to r, right? So I can apply the Taylor's theorem to that. Supposing, of course, that g is a smooth function. But I'm assuming f is smooth, okay? So assuming f is smooth, r is linear in t. It's definitely smooth. So I can certainly apply Taylor's theorem to g. And so Taylor's theorem would look like this. If I look at the Maclaurin series, for example, I would have what? I'd have g of 0 plus what? Plus like g prime of 0 times t plus 1/2 g prime prime of 0 times t squared plus like 1/3 factorial g prime 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 of 0 times t cubed, and so forth, right? All right. So I guess I'm going to leave myself this space here to plug in what I have there. G of 0 would be what? F of R of 0. R of 0 is x naught. So this first term is just f of x naught. We can get that out of the way. Okay? And then, well, what comes next? Well, we need to work that out. All right? So what is g prime of t? And I'm going to get this, I'm going to just erase that here, make myself some room. So g prime of t is d dt right, of f of r of t. Now, do you remember what the chain rule is here?
F prime of r.
Right. Well, yeah. Fair enough. F prime of r of t times r prime of t. But we can be more specific, right? It's the gradient of f, right? It's nabla f of r of t, right? Dotted with r prime of dr dt, right? Now, what is dr dt? Well, dr dt is exactly x minus x naught, right? So this is really the gradient of f at r of t dotted with x minus x naught. And that's a pretty nice formula if I plug in, so what's g prime of 0? See, g prime of 0, I can calculate from that. G prime of 0 is just going to be what? It's going to be the gradient of f at x naught, right? Dotted with x minus x naught. I can see that from here because when now I think it may be in our best interests to take a more summation notation approach from going this point forward. So let's just calculate g prime of t. Let's not really calculate anything. Let's just rewrite g prime of t as, in fact, the sum, right? I equals 1 to n of partial f partial xi at r of t, right? Times what? Times x sub I minus, I'm going to use a superscript here if that's okay with you. X upper I minus x sub 0 upper I. Those are not exponents. I'm just changing the superscript notation so that it's easier to see there. So there's my g prime. So then what do I do? Well, I differentiate again. What's g prime prime of t? Well, you see it's going to be the sum I equals 1 to n of d dt, right, of this and then times x upper I minus, I guess I can do the sub I. You know what I'm going to do, if it's okay with you? I'm going to put the I lower because it's less weird. And I'm going to put the 0 up here for the sake of getting out of the way. As I don't want to write a double subscript because that's just annoying. All right, like that. Now that's not part of the differentiation, right? The differentiation is just, because that's a constant. So I don't have to differentiate that. So then what? Well, that's again a chain rule. See, so this would be, I could write it as the gradient of partial f partial xi, right? Dotted with, dr dt. But I probably would do better instead to write it in summation notation. So let me not do that. Let me stick with the summation notation way of writing the chain rule. So what does the chain rule look like in summation notation here? So I've got the sum over I equals 1 to n. The sum over j equals 1 to n, right? And I'm going to have partial x sub j of partial f partial x sub I, right? Times what? Times x sub j minus x sub j naught, because that's the dr/dt term. If you like, of course, I could write it as, I could make another step here. I could say, well, that's really dx, dxi dt, right? And dxi dt is xi minus, that's a j rather, dxj dt, right? Anyway, so cleaning it up a bit, what we have, and of course this is where, this is evaluated where, at R of t, right? So, long story short, we see that g prime prime of 0 is, in fact, the sum over I and j equals 1 to n, partial squared f, partial xi, partial xj, at the point x naught times x sub I minus x naught sub I times x sub j minus x upper naught sub j. Now, no matter how many times I differentiate, there's no time dependence in this when I look back up here at this formula, right? So we just keep chain rolling. Like next we'll chain roll the ijth derivative. Right, like the next one would be like, we end up with like ddt of, the next calculation up, we'd have like ddt of partial squared f, partial xi, partial xj at R of t, right? And that will end up giving us like the gradient of this thing, right? At R of t, dotted with, again, x minus x naught. I mean, it's that same chain rule every order. So every time we're just pulling down, we keep partial differentiating, partial differentiating, partial differentiating, and you start to see the pattern, right? So let me just kind of say what this is going to come to. This is going to come to the sum k equals 0 to infinity of 1 over k factorial, the sum I1 dot 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 ik equals 1 to n, all right, of partial k f partial xi1 partial xi2 partial xin, not in, but ik times x xi1 minus xi1 up, the naught, and so forth, dot 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 dot, times x sub ik minus x, the ikth component of x sub naught, and there you go. That's the multivariate Taylor series expansion. Now I should be careful. That's just g of t. Actually, we're not quite to the multivariate Taylor expansion. So how do you get the multivariate Taylor expansion? My bad. I should have one more step, right? T equals to 1. See, putting t equals to 1 gives me f of x. So then that gives me f of x. Pull that out. And of course, these are here x. X of I1 is a component of x and so forth. So yeah. That's it. So it really is just a straightforward consequence of the regular Taylor's theorem and just the chain rule repeatedly.
Do we do this in Calc 3 or no?
I do, but I don't think it's in Stewart. I didn't learn it until grad school because I studied Calc 3 out of Stewart and it wasn't there.
Yeah, I use Stewart.
So I don't think it's in Stewart actually.
Not this one, the other Stewart.
The other.
Stewart has two versions of his calculus. One is like analytic, early transcendentals, and the other.
Oh yeah, I think the early transcendentals versus the not early transcendentals, it'll be more or less the same, but the
I've heard it's just the order of the topics.
Yeah, let me look here. I gotta find your course planner. I will find it eventually.
I have it here.
So, I mean, of course, at this point, we can look at examples of this, and maybe we should do that a little bit. But I just wanted to see where I was in terms of our plan. Okay, so we're pretty much on track then. That's good. Let's see here. So, man, I got to come up with some examples.
Are you gonna have the test two already?
The test what?
Test two of differentiation.
Is that what it is?
Yeah, that's 24 October.
Yeah, once we get the test 2 would cover this, and there's one more topic that's on test 2, which is the variational calculus. So let's see, do we meet Wednesday? I'm trying to remember. No, we have a Tuesday. We have tomorrow, but then we don't have Thursday, right?
Yeah,
That's correct. Okay. So, all right. So let me just show you at least a token example of this or two, and then we'll go on. Okay. Actually, let me kind of make some up here. So, oh, I remember what I was going to do. I'm, if I hadn't done this right now, I'd be kicking myself later, Ernesto. I tell you what. I'm at example 2. Yeah, example 2, right, for today, I guess. I just remembered what I was going to do. I'm a dummy. Oh, duh. I mean, yeah, I want to show you an example or two that we use this combined with the other idea, right? Like that's kind of the point here. So let's see here. How about this? We'll look at f of x, y, z equal to 13 plus, 2 times x minus 1 plus 4 times z. All right, plus x minus 1 squared plus y minus pi squared plus z squared. All right, plus dot, 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 dot. So suppose you're given that. So this is a very low-level question. And I guess I should probably write out, over here, like what we're looking at is, of course, f of x naught, right? And then we've got like plus partial f partial x1 at x naught times x minus x1, x naught 1, right? x1, da, 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 plus partial f partial xn at x naught times xn minus x naught n. I'm kind of tired of writing it in this notation. I'm going to drop to 2 dimensions, okay? So f of xy be like f of the point plus partial f partial x at the point times x minus the let's suppose that the point is a comma b, okay? And let me just drop this of naught on the point. So the point, all right. So x minus a plus partial f partial y evaluated at the point times y minus b plus 1/2 partial squared f partial x squared at the point times x minus a squared plus 2 partial squared f partial x partial y at the point times x minus a times y minus b plus partial squared f partial y squared at the point times y minus b squared. Let me get rid of this little, we're past that part, so I'll erase that. There we go. All right, and then what comes next? Then like third order stuff, right? So like next there's, yeah, 1 over 3 factorial. Yeah, f x x x at the point P times x minus a cubed. And then you've got, 3 fx xxy at the point P times x minus a squared times y minus b. And then like plus fxyy, 3fxy at the point x minus a times y minus b squared plus fyyyy at the point P times y minus b squared plus dot dot dot. Well, no, there's no plus dot dot dot, just close parentheses, right? Then the plus dot 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 dot. So I think if you sort through it, am I missing something? Or is that it? I think that's it. See, as you go on, you're going to get binomial coefficients. Like 1, 1, 1, 1, 1, 2, 1, 3, 3, 1, 1, 4, 6, 4, 1. I think you're going to get binomial coefficients as you go up. Like if I looked at the quartic term, I would have like, let me write it out. 1 over 4 factorial, right? And then I believe I would get a f x x x x at the point P x minus a to the 4th power, if I'm not wrong, 4 f x x x y at the point P x minus a to the 3rd power times y minus b. But then you got your plus 6 f x x y y at the point P times x minus a squared times y minus b squared plus 4f x y y y, as in why am I doing this, x minus a y minus b to the 3rd power, and then finally f y y y y of point P times y minus b to the 4th power, and then finally the plus dot dot dot. So yeah, wonderful. This plus is continued over here. So there you go. That's the multivariate Taylor expansion for a bivariate function out to order 4, if you ever wanted such a thing. I do not ask Calculus 3 questions about the meaning of these kind of coefficients because it gets kind of combinatorial and. But anyway, now going back to my example, we can ask interesting questions, which is like, is it a critical point? Right, so a critical point would be one where the gradient is 0, right? And like, so for this one, no. Well, first of all, what my expansion is about what point here?
1.
So 1, that's part of it.
Sorry.
This is a function of 3 variable.
1 pi 0.
Yeah, 1 pi and 0, right? And so you can see that the gradient of f at the point 1 pi 0 is equal to 2, 0, 4. So apparently it's not a critical point, right? You can see there's other easier things, like what is f of, here's the lowest hanging fruit. What's the value of the function at the point? Well, 13, right? What else can I tell you? Well, I can tell you the xx derivative at the center point is in fact equal to 2, because 1/2 times whatever's here has to be, you see, in order to get a 1 there, I have to have 2 times 1/2 to give me a 1 there, right? And likewise, like that's also equal to fyy at the point of expansion. And it's also equal to apparently fzz, right? At the point of expansion, because I made the coefficient of all of those 1. But on the flip side, assuming that what I mean here is that this is to order, 2, that's everything to order 2, okay? Assuming that's the case, then you can tell me what is fxy, what is fxz, what is fyz at the point. Zero, right. So I don't know. I think these kind of questions are kind of fun. They don't really require calculation. They just require interpretation. Every time I ask them in Calc 3, there's like 40%, 50% of the class who just differentiates everything. They don't try to understand well, I don't know. I can't. Let me not question their motives. So example 3. How about this? What if we had f of x, y, z, w equal to 300 plus, let us say 2x squared plus or minus 2xy plus 2y squared plus 13z squared plus 14w squared, all right, plus dot 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 dot. So this is the, expansion about 0, 0, 0, 0 to order 2. Now my question is this a local minimum? Is it a local maximum? Is it not a local extrema at all? Like, what can you say about the origin here? So for this one, we can just look at it and go, aha, well there are no linear terms. So by inspection, we see that the gradient of f at the origin is the 0 vector. So f of 0 equal to 300 is possibly a local min-max. Right? So then, well, what's the story? So you look at it, and what we've got is we've got f of x, y, z, w, right, is equal to 300 plus a quadratic form in the x vector, let's say, right, plus dot, 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 dot. And so close to the point, close to the critical point here, the behavior of this function of 4 variables is completely dominated by that quadratic form piece. But we can understand this quadratic form because it has a matrix of what? We can see it. It's 2, minus 1, minus 1, 2, 13, 14, right? But from the calculation we just did a bit ago, we know that this matrix has eigenvalues 1 and 3. So we can actually write down V1 is like, 1 over root 2, 1, 1, 0, 0. V2, 1 over root 2, minus 1, 1, 0, 0. V3, 0, 0, 1, 0. V4, 0, 0, 0, 1. That's an orthonormal eigenbasis for this matrix, exploiting the calculation we did in example 2.
And when you say
example, oh man. This is 3, isn't it? Yeah. You were going to tell me that a while ago. I didn't listen to you. There we go. Fixed it.
So when you say dominated by the quadratic form, the other terms?
Right, think about that. So if we're close to the critical point, the terms we're not writing down have order 3 or order 4 or order 5, whatever. So think about this. If the largest magnitude, if you're within a ball of, say, radius 0.1, the largest, like, the value for one of the x, y, z, or w's can be is like 0.1. So 0.1 squared is like 0.01, but what's 0.1 cubed? is much smaller, and 0.1 to the fourth smaller still, right? So it's completely dominated by the lowest order terms close to the point of the expansion. So this is the same trick that makes power series useful in Calc 2, right? Close to the point of expansion, the higher order terms are vanishing. So listen, the point here is if we use eigencoordinates for this, then f of x bar, y bar, z bar, w bar, and x bar, z bar and w bar are just z and w in this case. They're already fine. The formula is already fine in z and w, but this will become, if I remember right, x bar squared plus 3y bar squared plus, well, 13 z bar squared plus 14 w bar squared, right? That's the formula for f in terms of the eigencoordinate system. And I forgot to add my 300, right? That's still there. My bad. And then plus stuff. But obviously this dominates, right? So like f of 0, 0, 0, 0 is 300. Is that a local min or a local max? Local min, that's right, because if you go away from the origin, you're adding this term. Right, now if you had the situation where you've got one positive and one negative eigenvalue, well then it's neither a max or a min, it's like a saddle. If they're all negative, it's a local maximum, because if you go away from the center, you're dropping down. Now I can't visualize this, but linear algebra picks up where I can't see things. I can calculate things still. Now, all right, so there we go. There are some better examples in the notes with like interesting formulas and stuff. I'll let you read those, okay? But I want to focus the rest of my attention on for today is Calculus 3. What did we learn in Calculus 3, and can we derive that now? Do you remember what we learned in Calc 3? So you have critical points, right? And we had the second derivative test, right? What did the second derivative test say? Do you remember it? It's easy enough to forget it. We never use it after that course, do we?
So it's related to maximization, minimization.
Right, yeah. What did the second derivative test say for Calc 3?
If it's equal to 0, it's either it's a local extrema.
Yeah, if we had f of xy with fx of ab equals to fy of ab equals to 0, and the second, second derivatives, fxx, fxy, and fyy also exist at ab. Right, then number one, if d equals to fxx, fyy minus fxy is greater than, if it's less than 0 at ab, then f of ab is neither min nor max. All right, so if the big D is negative, then it was not a local max or min. It was like basically a saddle. The z equals f of x, y is saddle shaped near the point, okay? And then number two, if D is equal to, same thing, right? Same thing. If that's greater than 0 at the point, right, then case 1, if fxx at ab is greater than 0, then f of ab is local fill in the blank. And 2, if f of xx at AB is less than 0, then f of a comma b is local fill in the blank. So you can tell me what goes there. I don't know if you remember or not, but this is local min. This is local max.
And why is that?
Well, that's
X greater than or less than 0?
well, that's the second derivative test. Okay. Now you probably saw this in Calculus 3, and it is almost certainly the case it was not derived for you. It was stated, but not proved, right? I have a strong suspicion it was stated and not proved. I think I'm about the only person who's so stupid as to prove it in Calc 3. So, and the reason I can prove it in Calc 3 is because I talk about the multivariate power series, which is where the proof naturally follows from. See, so here's the proof. Is that, given that the gradient of f at AB is equal to 0, we have that f of x comma y, right, is equal to f of a comma b plus what? Plus 1/2, right? fxx, I shouldn't have erased that, oh well. X minus a, we only need this much of it though. Okay, so x minus a squared plus, 2 fx y at a comma b times xa times y minus b, right? And then plus fyy at a comma b of y minus b squared, right? Plus dot 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 dot. So the behavior of the function at the critical point is dominated by the quadratic piece, right? So let us save ourselves the hassle of writing x's and y's here, and let's just call this whole thing q, q of h comma k. All right, where here I'm going to say h is x minus a and k is y minus b, okay? So if you look at that, we've got q of hk is h comma k times what matrix? Well, times the matrix fxx, fxy, fyxy, fyy times hk, right? And I'm going to suppress the, this of course is all at a comma b, but let me just not write that explicitly. Okay, and we know this is a symmetric real matrix. We can apply the theory of quadratic forms. What are the eigenvalues? See, this is where it gets interesting. This is why n equals to 2 is so special. N equals to 2 is so very special because n equals to 2, if I have the matrix A equals to A, B, C, D, right? Then I know a couple things. I know that the trace of A is A plus D, but it's also equal to the sum of the eigenvalues. And here I know that they exist in the real by the real spectral theorem, okay? But I also know that the determinant of A is the product of the eigenvalues, right? But what, so, okay, so this equals to what? Well, this, by the theory of quadratic forms, this is plus what? Plus 1/2 what? Lambda 1 h squared plus lambda 2, well, not h squared, but h bar squared, right? Lambda 2 k bar squared, right? So, and they're basically different cases, right? So if lambda 1 and lambda 2 are both greater than 0, local what? Local min, right? If lambda 1 and lambda 2 are both less than 0, it's a local max, right? And if you got lambda 1, lambda 2 is less than 0, saddle. In other words, z equals to f of xy has slope. Okay, so wonderful. But what is the determinant of the matrix of Q? See here? So what's this? This is exactly fxx fyy minus fxy squared. That is equal to the product of the eigenvalues of the matrix. So that shows you why there are either the d less than 0 saddle or d greater than 0 min max. It remains to understand this, what you were more curious about, which is what gives with these conditions, right? Well, check this out. A plus d is what? A is fxx, and d is fyy. Right? And that is the sum of the eigenvalues, right? So think about that. That is either, so let's talk about these two different cases, right? Like, let's call this case 1, let's call this case 2, right? So for case 1, they're both negative, right? So we have fxx plus fyy is less than 0. Case 2, we have fxx plus fyy greater than 0. Notice that, well, suppose they had a different sign. Suppose that the signs of fxx and fyy were different. What if, like, one was positive and one was negative? Would that be a problem? I'm not sure I see it right offhand, but if we study it carefully, we can see that they both have to have the same sign. Like the most natural condition for case 1 and 2 to put would just be that the sum of the double derivatives is positive, or the sum of the double derivative is negative. But you can just check the xx derivative. So we know that their sum is either negative in case 1. And what else do we know? We know that the product of the lambdas, we know the product of, it's just that. The product of the lambdas is what?
It's positive.
It's positive. But the, yeah. Well, let's just look at the algebra problem here for a second. You've got what? You got, on the one hand, you've got lambda 1. You have lambda 1 plus lambda 2 is fxx plus fxy, right? Fyy, right? But you also know that lambda 1 times lambda 2 is fxx fyy minus fxy squared, right? Trying to think if I can I solve these? Can I solve these equations for fxx and fyy? Maybe not. I've got 1, 2, 3, 4. I got 5. No, it's too much. It's too much. I can't convince myself why it should be, but there is a reason that this necessarily implies that both fxx is less than 0 and fyy is less than 0. And this also implies that both fxx is positive and fyy is positive.
Well, but if they have to have the same sign and sum is negative, shouldn't they both be negative?
Didn't I write that?
But no, isn't that the reason why that implies that? Because we know they have the same sign because their product is positive in case 1 and 2.
But the product is not positive. The product is the product positive?
Because if it's
See,
negative,
but hold on. Oh. So I'm sorry. What I'm not seeing, Ernesto, and I should be seeing, is that fxx, maybe I still don't see it, fx, the product of the second derivatives is not equal to the product of the eigenvalues, which is what I'm tempted to think. It's the product of the eigenvalues plus the fxy derivative squared, right? Oh, okay. So if, oh, fair enough. So if they're both, well, son of a gun. Well, this is definitely a square, right? So, all right, fine. Case 1. They're both words. They're both negative. Both eigenvalues are negative. Then this is definitely positive. Therefore, they can't have different signs.
and same in case 1.
Same in case 1. Okay, that's the argument. I'm a dummy. Now, I actually have a derivation of the second derivative test in my Calculus 3 notes where I derive it using Lagrange multipliers. So what I do is I look at an arbitrary quadratic form on the circle and I derive these formulas for the Hessian, this matrix. This is the Hessian matrix. I derive the formulas for the Hessian matrix as Lagrange multiplier conditions on a little circle. And from that I work it out. So like there is a way to get at this theorem without using the full force of multivariate power series or anything, but I find this proof to be most natural. It's just the statement that the quadratic form is dominating, and how does the quadratic form behave? Well, we look at the eigenvalues and it reveals everything. It just so happens that for functions of 2 variables, this formula is something we can share with students, right? It's not bad. For functions of 3 variables, you won't find a 3-variable second derivative test written in a calculus book, because the relation between eigenvalue 1, you still have the equations, the trace of the matrix is lambda 1 plus lambda 2 plus lambda 3, and you still have the determinant is the product of the eigenvalues, but it's not so nice to sort out the relation between the 3 eigenvalues. And the 3 eigenvalues, okay, if they're all positive, it's a minimum. If they're all negative, it's a maximum. And if there's a mix, it's a saddle. You could write that down. It wouldn't be impossible. You'd have to look at the matrix for the 3-variate would be like this, right? You could just write basically the determinant. The condition would just be this. If you look at this matrix right here, this 3-variate Hessian matrix, if its determinant is negative, it's a saddle. If its determinant is positive, it's a local max or min, assuming you're at a critical point. But then sorting out which is the max and which is the min would be a little bit more involved. But I guess it's kind of interesting to think about how would you actually hack through, lambda 1 plus lambda 2 plus lambda 3 equal to the, you'd have, getting us started, lambda 1 plus lambda 2 plus lambda 3 equal to what? Fxx plus fyy plus fzz, right? You'd have that's equal to that. And you'd know that but the determinant here is, it's so much nastier, right? It's like fxx times fyy fzz minus fyz squared minus fxy times fxy times fzz minus fyz times fxz, and then plus fxz times fxy minus fxy fyz minus fyy fxz. Like, it's just a mess. And at the end of it, I would just rather hold off and say, students, learn linear algebra first, and then you do it, right? Because you need linear algebra to understand the problem properly, is what it boils down to. But yeah, so that's multivariate extreme. That's like what I have to show you about, how to do multivariate extrema. Basically, the tools in my toolbox are Lagrange multipliers, and then, for local behavior, replace the function by its multivariate power series, and that's a pretty good way to simplify a problem. If it's complicated and nonlinear, we can replace it with a bivariate or a trivariate polynomial, and that's easier to work with. Other tricks include just like substitutions, right? Like if you've got a formula that involves something that is just, if there's like an x squared plus y squared plus z squared square root all over the place, then maybe you should call that rho. Maybe you should change the spherical coordinates, right? That's the other important trick for actually solving real problems, is making substitutions of appropriate variables. Like, that's always a thing. But I don't know if there's really is there a general theory of that? Well, I suppose there is. That would be symmetries, the study of symmetries. Symmetries in differential equations, for example, is an interesting topic, which I only partly understand. It's on my list of things to understand better. I've tried a couple times with a couple students. It just never quite finishes. Let's see here. Any questions? So next up, I want to talk to you about words. Lagrangian mechanics. So the next topic is variational calculus. So in variational calculus, we're going to, it's again optimization, but now instead of us looking for a point or something where we're finding a maximum for a function, we're looking for a function which maximizes some kind of quote-unquote functional. A functional is a function of functions. So for example, integration. You could use like integration to set up a functional. You can ask the question like, well, here's a question we could ask. Can I erase?
Yep.
You good? Okay, good, yeah.
I'll look at the video.
You good?
Yeah.
So, here's a problem. You've got a point here, right? And you got another point over here. And the question is, if you think about all possible paths which go from there to there, minimize the length. Now this is a kind of dumb question because you know the answer already. You know how to minimize the length of a path going between 2 points in the plane, right? But to do that, we can look at the Lagrangian of y. Well, let's say of xy. All right? And that would be the integral over the square root of like x dot squared plus y dot squared dt. And I can just choose to parameterize my paths going from 0 to 1 just to keep things simple. All right. So this would be an example of a functional because the arc length depends on the particular function you're putting in. Like here I mean x and y to be functions of t. So this is a, or if you wanted me to take a more like one-dimensional approach, we could say it's really just y, L of y, and perhaps y prime, right? And then we could just do integral from 0 to 1. Well, we can do integral from x1 to x2 of the square root of 1 plus dy dx squared dx. This would be how to set up. Here, I'm assuming that these 2 points are not vertically situated. I want x1 to not be equal to x2. So I can either, and technically speaking, I really should have an x dot and a y dot here. So the Lagrangian, it's going to be a function of a path and its derivatives. All right? But it's a functional in the sense that if you give me a different function, I get a different arc length, right? Now, as I'll derive for you next time, we can write down what are called the Euler-Lagrange equations. So the Euler-Lagrange equations, and yes, it's that Euler, and yes, it's that Lagrange. These guys, man, good grief. And so, like in the y formalism, it looks like this: partial L partial y is equal to d dx of partial L partial y prime. That would be, there's a single Euler-Lagrange equation for that one. And so, like this, oh my bad, I said L, but that's wrong. This is actually S. This is the action. Sorry, I'm a little fuzzy. So the thing inside the integral is actually the Lagrangian. So like here, my Lagrangian of x and y is actually just the square root of x dot squared plus y dot squared. And over here, L of y, let me just say L is equal to the square root of 1 plus, I probably would be better to say y prime squared here, okay? Just to make what I'm about to write more coherent. So, okay, great. Well, what's partial L partial y? Well, there is no y dependence there, so that's just 0. And then you got d dx of what? Well, 1 over the square root, twice the square root of 1 plus y prime squared times 2y times 2y prime. Okay, so then that if that's equal to 0, that says that y prime over the square root of 1 plus y prime squared is equal to a constant. All right, and then you can go on and try to solve that. I don't feel like trying to solve that at the moment. I'm going to go back. So that's the one formalism. I actually prefer the parametric formalism because in the parametric formalism, there's 2 Euler-Lagrange equations. The one Euler-Lagrange equation would be partial L partial x is d dt, partial L partial x dot. And the other would be partial L partial y is d dt of partial L partial y dot. And actually, you know what? Just to make our life easier, I'm going to erase that square root and just say we're going to minimize, we're going to look at like the speed squared as the Lagrangian. That'll make life easier. It would have made it easier down here too. Let me do that. Sorry. If I do that, then I think I can actually hack through this pretty easily. Because then instead of this partial L partial y prime just become what then? It just becomes 2y prime, right? So in other words, you get y double prime equals to 0. Integrating twice, we get what? Of course, the answer is a line. Now, from the parametric perspective, we get equations 0 is equal to d dt. What's partial L partial x dot? Well, 2x dot, okay? And 0 is equal to d dt of 2y dot. See, so again, we get x double dot equal to 0 and y double dot equal to 0, right? Which integrating twice gives me x is equal to like, x naught plus tx1 and y equals to y naught plus tx2, y2 rather, right? And of course, if we look at these,